guys, welcome to lesson 8. We are going to be exploring today multiples and factors. So multiples and factors are similar to each other. And first we're going to go ahead and review some of our multiplication language. So you may remember from last year learning about multiplication that you have a factor is one of the numbers that you multiply to get your answer to your multiplication problem or your product. Now you will notice that I wrote up here factor twice, and we know that that's true because one of the properties of multiplication is that commutative property that allows us to change the order of the factors and still get the same product. So that's why we have factor twice, right? Because we have one factor here, we have another factor here, but we can just as easily swap them around and still get the same product. So it doesn't matter which one it comes first. They're both factors that when multiplied together will get us a product. Now, with division, it would be different, right? Order does matter when we divide. And so we would not be able to call them the same thing because the one that comes first is going to be important in changing the meaning. So for example, if I have 9 divided by 3, I'm going to get 3 as my answer or my quotient, which is called the answer to a division problem. And I have my dividend and my divisor. Now, if I switch my dividend and divisor, I no longer have an equation that works. So that's why we have different names for each of the numbers in a division problem. But in multiplication problem, we can keep them the same because order doesn't matter when we multiply. Okay, so when you have a multiple, though, a multiple is a pattern that you might have. I've been working with the 3rd graders on building a multiplication chart, and a multiple would be an example of something that shares a factor. So for example, you'll notice down here for the tens facts, we have 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Those are all those are all multiples of 10 because you multiply some number by 10 to get those products each time. So for 10, we get 10 times 1, right? So for 20, we have 10 times 2. For 30, we have 10 times 3. So we're changing one of the factors, but one of the factors is staying the same, and that's 10. So we call those multiples when one factor stays the same, and we get products that go along with the same factor. All right, so let's go ahead and jump right in. Please go ahead and turn to page 143 in your packets. And you'll see that there's a problem that says a garden has several rows of pumpkin plants and each plant has 10 rows. How many pumpkin plants could be in the garden? Well, it's funny that we just used 10 as an example because it doesn't tell us, it says each row has 10 plants, but it doesn't tell us how many rows, right? So if I had one row of 10, close those little pumpkins up. If I have one row of 10, then I would have 10 pumpkins, right? If I added a second row of pumpkins, I'm still going to have 10 pumpkins in the row. But now instead of 10 pumpkins, I now have 20 pumpkins, right? If I had 3 rows of pumpkins, I still have 10 in my 3rd row, but now I have 30 total pumpkins. So each time I still have 10 in a row, but I don't know how many rows I'm having. So really it could be any multiple of 10. Now let's go ahead and look at page 144. Number 1 says, how can you describe how many pumpkin plants there could be? So one way that we could talk about that, if we weren't super comfortable yet using multiples, is we could say we could have any number of rows times 10 to get the total number of pumpkins, right? So any number times 10 is going to equal the number of pumpkins. Now I'm using this not as a hashtag, not hashtag of pumpkins. Oops. Here we go. But I'm letting this symbol stand for number. So this is a really fun symbol that can be used for a lot of things. You guys probably know it more as a hashtag these days on Instagram, but it also used to be a pound sign on old telephones, like when I was growing up. And now, but it also stands for number. So we can go ahead and instead of writing out the word number, we can just go ahead and let that little symbol stand for number of pumpkins. So we have any number times 10 is going to get you your total number of pumpkins. And in fact, if I want to make this a little bit more algebraic, instead of using a question mark, I'm going to use P for the number of pumpkins, right? So pumpkins times 10 is going to be the total number of pumpkins. Actually, to make it more accurate, I should really use R for rows. Number of rows times 10 equals number of pumpkins. Okay, we're going to look at number 2 where it says look ahead. It says you can extend your thinking about multiplication by looking at factors of a number. Factor pairs, multiples, prime numbers, and composite numbers are all things we're going to be talking about in this lesson. A says a factor pair is two numbers that are multiplied to give a product. So factor times factor equals product. Excuse me. So when we have two numbers, excuse me again. When we have two numbers that multiply together, we have two factors, right? And so that's going to be called a factor pair. So let's just go ahead and experiment with some factor pairs. You guys already know these because you are so good at multiplication. So let's say I say 2 and 1 are my factor pairs. I know that I'm going to get 2 as my product, right? If I have 3 and 3 as my factor pair, I'm going to get 9. If I have 5 and 6 as my factor pair, I'm going to get 30. Now 30 would also share a factor pair of 3 and 10, right? Because we can also multiply 3 times 10 to get 30. And it would also have a factor pair of 30 and 1 because any number times 1 is going to be itself. So a number of products can have more than one factor pair. So looking at A again, it says since 1 times 20 is 20, a factor pair of 20 is 1 and 20, right? So because we can multiply 1 times 20 to make 20, 20 would have a factor pair of 1 and 20. And you may have noticed that how I wrote my factor pair is I'm grouping them together using those parentheses and I'm separating them by a comma because if I didn't have my comma, it would look like 120, right? So commas can be really important when we're using numbers. So a factor pair of 20 would be 1 and 20. If I were going to write more than one factor pair, I could also say that 4 and 5 would also be factor pairs of 20. Now, these are all numbers that we can multiply to get 20, right? We can multiply 4 times 5 or 5 times 4. Even though I have 1 and 4 both here, that doesn't necessarily mean that I'm multiplying those two together. It just means that these are all factor pairs of 20, all things that we can multiply by other numbers to get to 20. And if we really wanted to be specific, we would probably separate them. Yeah, that's definitely a better way to go so that we can see the factor pairs that make up 20. All right, B says to fill in the multiplication equations to show the other factor pairs of 20. Well, we just kind of did that. We have 4 and 5 And one that we didn't show is we have 2 and 10 also make up 20, right? So C says, what are 6 different factors of 20? So they're just asking you to list them. So for 20, we have 1, 2, 4, 5, 10, and 20. Now I've listed them out from least to greatest, and you'll notice that there's kind of a pattern here. 1 times 20 is 20, 2 times 10 is 20, 4 times 5 is 20, 5 times 4 is also 20, 10 times 2 is 20, and 20 times 1 is 20. So our pairs kind of go together if we line them up from least to greatest. All right. D says a multiple is the product of a given number and any other whole number. So as we talked about, if I were doing multiples of 10, I would have 10 times one number, in this case it would be 2, to make 20. But then that's not just a multiple by itself, that's just a multiplication fact. But then if I said I also have 10 times 3 is 30, 10 times 4 is 40, 10 times 5 is 50, these would all be multiples of 10 because 10 is what they all have in common as one of their factors. The other numbers are changing, 2, 3, 4, 5, 6, 7. We could keep going, right? But these are all multiples of 10 because they all share 10 as one of their factors. Just like in our pumpkin problem. We had 10 pumpkins in each row, but we could have any number of rows of pumpkins. All right. We're going to go ahead and skip filling in D. But E, I want to bring up because it says a number with more than one factor pair is called a composite number. And a prime number is a number that only has one factor pair. Okay, so what does that mean, right? That's all a bunch of confusing math talk, teacher Jess. So composite, think back to 2nd grade when you learned about composite words, right? So composite words are words that are put together from 2 other words. Composite numbers come when we have more than one factor pair. So for example, if I use my example of 20 again, I had 1, 2, 4, 5, 10, and 20 were all factors that I could multiply together to make 20, right? So 20 would be an example of a composite number because it has more than one factor pair. Now, all numbers have at least one factor pair because remember, any number times 1 is going to be itself. So for example, if I use 7, I can say I have 1 and 7, that when I multiply them together, that's a factor pair that would make up 7, right? But let's see if I can come up with any other numbers that I can multiply together to make 7. I know I can add other numbers to make 7, but can I multiply any? So I've started with 1. Is there any number multiplied by 2 that will make 7? No. Any number times 3? No. Because if I count by 2s, I go 2, 4, 6, 8. So 6 and then 8, so it skips 7, so that won't work. 3, 6, 9. Oh, I skipped from 3 to 9, so 3 won't work. 4, I have 4 and then 8. Oh, definitely won't work. 5, 5 and then 10. Nope, each time I'm skipping over to, I'm skipping 7. 6, I would have 6 and then I would have 12, so that doesn't work. 7, I would have 7 and then I would have 14, and I've already had 7 here. So by the time I get to the end here, by the time I get to that number, I'm all out of options. There are no other numbers. I have just confirmed that there are no other numbers that when multiplied together will make 7, because I obviously can't multiply numbers bigger than 7 to make 7, because when we multiply, we increase our numbers. So if I had numbers larger than 7, if I tried to multiply 10 times 10, or even 10 times 1, 10 times 1, that's the smallest multiple that I can make. It's going to equal 10. That's still larger than 7. So I can't make any numbers with 7 except for 1 and 7 as a factor. Now that means that 7 is what we call a prime number. So prime numbers are numbers that only have one factor pair, and that factor pair is always 1 and the number itself, because we can always multiply a number by 1 to get itself. But if I can't multiply any other factor pairs, then that number is going to be prime. So they have a question for E. It says, there is only one way to put 11 pumpkins in equal rows, because, so would 11 be a prime or composite number? So what they're saying is, we have 11 times 1 is going to be 11. Are there any other ways, any other numbers that we can multiply together to make 11 total pumpkins? Let's see. 2, 4, 6, 8, 10, 12. Nope, I skipped 11. 3, 6, 9, 12. Skipped 11 again. 4, 8, 12. Skipped 11 again. 5, 10, 15. Skipping 11 again. 6, 12. Oh, definitely skipped over 11. 7, 14. Skipped 11. 8, 16. 11. 9, 18. 11. 10, 20. Skipping 11. So 11 times 1 is the only factor pair that I can have for 11. So that would make 11 another example of a prime number. Okay, so let's go ahead and turn a couple pages. Actually, on page 145, there's some vocabulary that we just talked about. So I think it's valuable to fill that, a valuable exercise to fill that in. So you'll see that there's a word, and then in your own words, and then an example. So the first word is factor pair. A factor pair are two numbers multiplied, right? So we have two numbers. A pair means two of, and factors are numbers that we are multiplying. So two numbers multiplied together. An example would be we have 2 times 2. That would be our factor pair. Okay. Next word is multiple. The multiple are the product of factors with one factor that stays the same. So for example, when we said we had multiples of 10, 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, 10, 20, and 30 would all be multiples of 10. They are all the products of factors with one factor that's the same, and that one factor that's the same is 10. Next word is prime number. A prime number only has one factor pair. So for example, 11, we said, can only be created by 1 and 11, or 1 times 11, or 11 times 1. That's the only factor pair that we can multiply to get the number 11. Okay? The composite number has more than one factor pair. They might only have 2, but they have more than 1. So for example, 12, we could get by multiplying 3 times 4, 2 times 6, or 1 times 12. And so we would have more than one factor pair that could make 12. Okay, now let's really actually skip. So go ahead and turn to page 148. The problem at the top says Leona has 5 cups of oats. There we go. Leona has 5 cups of oats, and she needs 2 cups of oats for 1 full batch of oatmeal muffins. Can she use all of her oats by making multiple full batches of muffins? So she has 5 cups. All right, here's a little handle. So she has 5 cups of oatmeal, or of oats rather, and she needs 2 cups for 1 batch of oatmeal muffins. So that means that if we took these 2, she could make 1 batch of muffins, of oatmeal muffins. That's my muffin, right? So 2 cups to make 1 batch of oatmeal muffins. So that means I could also use these 2 to make a batch of oatmeal muffins. But I have 1 left over, right? So I had 5 cups. 2 cups will make 1 batch. So I have 2, 4, but then I have 1 left over. So maybe she could make a half batch, but we're not talking about half batches right now. We're talking about how many full batches can Leona make? Can she use all of her cups? No, she would still have some oats left over after making 2 full batches of oatmeal muffins. All right, so the first one under the problem says picture it. So you can use a picture to help you understand the problem. That's kind of like what I did here. And then the second one says that you can have a model too. So the model that they've used is a number line. So our number line is going to be marked, oh, actually, they've done a different number line than that. So they have their number line going all the way to 10. I'm going to have mine just go to 7. And it says you can count by 2s to find the multiples for 2s. So 2, that would make 1 batch of muffins, right? 4, that would make 2 batches of muffins. 6, that would make 3 batches of muffins. But we were at 5 cups. I skipped 5 when I counted from 4 to 6. So that means that I would not be able to use all of my cups to make a full batch. So the multiples of 2 are the ones that are circled. If I had another cup, I could make 6 full batches, or I'm sorry, I could make 3 full batches. But since I only have 5 cups, I can make 2 full batches, but I would still have some left over. Okay, we're going to go ahead and skip on over to page 150 to do some practicing with this. So on page 150, pause the video, go ahead and try problems 8, 9, and 10 on your own, and then restart the video to check your answers. All right, now that you've completed 8, 9, and 10 on your own, let's go ahead and go over it together. So problem 8 says there are 4 bottles of water in a pack. Okay, 1, 2, 3, 4 bottles in 1 pack. Patrick needs 20 bottles of water for his soccer team. Can he buy exactly 20 bottles in packs of 4? Show your work. So you may have chosen to approach this in different ways. You may have chosen to draw a picture. You may have chosen to do a number line. Since I started drawing a picture, let's start with a picture. So for 1 pack, I have 4, right? In a second pack, I would also have 4, but that would mean that I would have, there's 4 bottles, but with my other 4 bottles, I would actually have a total of 8 bottles, right? So 1 pack, 2 packs, 4 bottles, 8 bottles. 3 packs would be 12 bottles. 4 packs, 16 bottles. 5 packs, 20 bottles. So yes, Patrick can buy exactly 20 bottles by using packs of 4. He wouldn't have to buy any extra. He wouldn't have to have any left over. He could buy exactly 5 packs to get the 20 bottles he needs for his soccer team. All right, number 9, what are the first 5 multiples of the number 3? Okay, so remember, multiples are the products that have a shared number. So let's go ahead and use a number line for this one. And since we're talking about 3s, actually, I'm just going to go ahead and label my number line. Oops. Okay, so I'm going to go up to 11 on mine because that's about as long as my number line has gone. So it says, what are the first 5 multiples of the number 3? Okay, so we're going to be skip counting by 3s to find multiples of 3, right? Because we're thinking we have 3 times 1 is 3. Okay, so that's the first one. So that's 1 multiple of 3. 3 times 2 equals 6. So that's the second one. 3 times 3 is 9. That's the third one. Uh-oh. Can you see my problem? Yeah, I'm going to run out of room because I need to count by 3s, and I only have 2 more numbers. So I'm going to have to go ahead and extend my number line so that now I can have 3 times 4 equals 12. All right, so that's 4, but I need the first 5 multiples. I need to keep going. So I'm going to make them kind of small. 13, 14, 15. So the next 3 numbers, 15. 3 times 5 would be 15. And now I have my 5 first factors. Or I'm sorry, my 5 first multiples of 3. So if I were going to list them out, where it says solution, I would just write in 3, 6. I'm separating them by commas so that we don't get a really big looking number at the end. 9, 12, and 15. Okay. Now, I also used equations. So you could use a number line. You could also use equations to think about this. You could also use skip counting. You could use a number line for skip counting. These are all tools for how you can think about multiples and factors. All right, number 10, how can you tell if 24 is a multiple of a given number? Well, if you skip counted by numbers and you landed on 24, then you would know that 24 is a multiple of that number, right? So let's just go ahead and without a number line, because my spatial concept doesn't seem to allow for that. Let's just go ahead and list if we skip counted, would we get to 24 with a certain number? So let's go ahead and start. We know that counting by 1s, that's not really skip counting, right? So let's start with 2s, and we'll say we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, bingo, 24. So if I were to skip count by 2s, I would get to 24. So that would mean that 24 is a multiple of 2, right? Because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, 2 times 6 is 12, 2 times 7 is 14, 2 times 8 is 16, 2 times 9 is 18, 2 times 10 is 20, 2 times 11 is 22, and 2 times 12 would be 24. So if I can go through and land on a number, then I know that that number will be a multiple of one of those factors, and the factor that it has that's the same. So each time we multiplied by 2, so 24 is a multiple of 2. Okay. Pages 151 and 152 we will be covering in our practice session on Wednesday. Go ahead and skip on over to page 154. So we're going to go ahead and read the problem up at the top first. It says, Alfred is arranging 40 model cars into rows. He wants to put the same number of cars in each row. Find all the ways that he can arrange the cars. Okay, so underneath they have a model. You can use an array to help you understand the problem. And you can also use an area model to help you understand the problem. So the second model, it says, there are 2 ways that Alfred can arrange the cars in 10 rows of 4 or 2 rows of 20 to get the, to handle the 40 cars that he wants to line up. So, so there's actually quite a few different ways that we could pair up, or that we could arrange the cars so that they have an equal number of rows and an equal number of cars in each row to get to 40. So you can use models. That's definitely a great way. Area models can be really great because they can really help you think about it. So we could have one long row with all 40 cars lined up in it, right? I don't know if that's exactly 40, but you guys kind of get the idea. So that would be like saying 1 times 40. We would have an area model that's 1 times 40. We could also then have 2 rows, and each row would have 20 in it, right? So again, I don't know if that's exactly 20, but we're just using our imaginations here. So I would have 2 on one side and 20 on the other, because that would still total the 40 cars. So I would have 2 times 20 would be another option. Let's see, any number times 3 that would get us to 40? 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42. Nope, I skipped 40. So 3 would not be a factor that would get us to 40. Let's try 4. I know that 4 will work. So if I have 4 rows, 1, 2, 3, 4, then I'm going to have 10 in each row, right? Because 4 times 10 is going to get me 40. Okay, so that would be another area model that would work. Let's see if I could do 5. 5 rows. Yep. 5 rows with 8 in it, because 5 times 8 equals 40. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5, 6, 7, 8. Oops. There we go. 8. So I could also have 5 times 8 to get 40. So far, these are all ways that we can get up to 40. Now I'm going to go ahead and say, let's check, that's 5. Let's check 6s. 6, 12, 18, 24, 30, 36, 42. I skipped 40, so that one won't work. 7s. 7, 14, 21, 28, 35, 42. That one also skips 40, so 7 won't work. 8. Oh, I already have 8 as a factor right here with 5. So now that I'm starting to repeat, that's one clue that I've already gotten all the factors. So all the factor pairs for 40, we have 1 times 40, 2 times 20, 4 times 10, and 5 times 8. Those would be all the ways that Alfred could line up his 40 cars to have an equal number of cars in each row. Okay, we're going to go ahead and skip pages 155 and 156. 157 and 158 are going to be, again, practice pages for our section on Wednesday. So keep turning until you get to page 160. Yep, okay. So 160, the problem says Janae has 36 pennies, Nate has 23 pennies. Are the numbers prime or composite? So a refresher here. Prime means it only has one factor pair. And that factor pair is going to be 1 and the number itself. Composite means it has more than one factor pair. Okay, so it might only have 2 factor pairs, but that's still more than 1. It might have 6 factor pairs. There's some numbers that have a lot of factor pairs. But a composite number has more than 1 factor pair, whereas a prime number only has 1 factor pair. So let's start with Janae's 36 pennies. So let's think about ways that we can make 36. Well, we know that we can multiply 1 and 36. So I'm going to kind of do my rainbow in reverse here, okay? Is there a number that we can multiply by 2 to get 36? Well, yeah, because when I look at 36, I see 6, it ends in 6, and 6, when we divide it in half, will be 3, right? 30, oh, 3 does not divide nicely into half, but it's not 3, it's 3 tenths or 30. So is there a number that's half of 30? Yeah, 15, right? So I would have 15 plus 3 more, 18 would be half of 36. So if we multiply 2 times 18, I would get 36. Okay, so that's 2 factor pairs so far. So we can already rule out that 36 is going to be a composite number. Now, if I wanted to keep going, I could find more factor pairs. But for the sake of the length of this video, I'm going to go ahead and stop there because we've already determined that 36 is not prime. It has more than 1 factor pair. Therefore, 36 is going to be a composite number. Okay, now let's look at Nate. Nate has 23 pennies. Let's go ahead and think of our factor pairs. Factor pairs, there we go. So I have 1 and 23 that I know are going to be factor pairs because all numbers have themselves and 1 as a factor pair. Let's go ahead and try 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Nope, I skipped 23, so 2 will not work. 3. 3, 6, 9, 12, 15, 18, 21, 24. Nope, I skipped 23 again. 23 will not work. 4s. 4, 8, 12, 16, 18, 24. Boom, skip 23 again. So 4 will not be a factor. 5, 10, 15, 20, 25. Oh, skip 23. 5 is not a factor. 6, 6, 12, 18, 24. Boom, skip 23, not a factor. 7, 7, 14, 21, 28. Skip 23, not a factor. 8, 8, 16, 24. Boom, not a factor. 9, 9, 18, 27. Skipped it, not a factor. 10, 10, 20, 30. Not a factor. 11, 11, 22. So that's really close. But then my next one's going to be 33. So I skipped 23 again. 12, 12, 24. Boom, already skipped it. 13, 13, 26. Skipped it. 14, 14, 28. Skipped it. 15, 15, 30. Skipped it. 16. I could keep going, but I'm already making these jumps that each of these numbers, these higher numbers doubled, is going to get me past 23, right? So 25 is going to be higher than, or I'm sorry, 26 is higher than 23, and 26 is 13 doubled. There's not going to be any more factor pairs in here. I can just tell. So 1 and 23 are the only factor pairs for 23. That makes it, boom, prime number. It only has 1 factor pair. Okay? Now, On that page, they say that you can picture it, so you can use pictures to help you understand the problem, or you could use an actual model if you wanted to get 36 pennies and see all the ways that you could go ahead and make an array with your pennies. That would be an option. Doing the same thing with 23 pennies, you would find that you could not make an even number of rows. You would only have one option, which would be to line them all up in one row of 23. You can also model it. You can use area models to help you solve the problem, just like we showed on the previous page. We went through just by listing factors of each one. So all of those are valid tools that you can use. Go ahead and skip to page 162. Pause your video, do numbers 6, 7, and 8 on your own, and then restart your video to check. All right, now that you have completed numbers 6, 7, and 8, let's go over them together. So Mrs. Ronaldo picks up 17 playground balls after recess. She wants to put the same number of balls into each ball bin. What different ways can she put the balls into bins? Show your work. All right, so we have a bin. Now we know that we can put 17 balls into one bin, right? We also know that if we had 17 bins, we could also put one ball in each of the 17 bins, right? So we can see that we have factor pairs. Let's see if there's any other options. So if we had 2 bins, we would have to put, let's see, for 17 balls, we would have to put, let's see, 13 in one and 14 in the other. So that would be, she wants to put the same number of balls into each bin. So 2 would not be a factor. Let's try 3. So 3, we could do, let's see, if we wanted to put 5 balls in each, we would have 5, 10, 15. If we wanted to put 6 balls in each, we would have 6, 12, 18. Too high, so 3 won't work. 4 bins, let's see, I could do 4, 8, 12, 16, 20. Oh, so that would be 4. I'm sorry, I had 4 bins, right? So that would be 4. So that would be, 4, 8, 12, 16. So I would need one more bin, and that wouldn't work. So I couldn't put 4. Oh no, I'm sorry, I would have 4 bins. So let's put 5 in. 5, 10, 15, 20. Nope, that won't work either. Man, okay. 6 bins. I could put 12, 18, 20. Oh, no, I'm already too high. So I can tell that there's really only going to be one way that Mrs. Ronaldo is going to be able to put 17 balls equally into the bin. She can put 17 balls into one bin, like saying 17 times 1, or she can put 1 ball in each of 17 bins, or 1 times 17. So that makes 17 what? A prime number, exactly. So it only has one factor pair, 1 and 17. Therefore, 17 is a prime number. Oh, which is the next question, right? I wondered why you guys were so on it with that answer. Is 17 a prime number or a composite number? Show your work. So basically when it says show your work, I would just say that I would just explain yourself. 17 is prime because it only has one factor pair, 17 times 1 and 1 times 17. Number 8 says tell whether 18 and 19 are prime or composite and explain how knowing the factors of the numbers helped you decide whether they were prime or composite. All right, so let's take them one at a time. Let's look at 18. What are factor pairs for 18? And I'm going to list them out in using my parentheses, okay? So I know that I have 1 and 18 at the other end. Is there any number that multiplied by 2 will get us to 18? Yes, it would be 9. Any number multiplied by 3? Yes, it would be 6. Any number multiplied by 4? No. Any number multiplied by 5? Nope. And then we already have 6 here. So we have 3 factor pairs that would make up 18. That would make it composite, right? It has more than one factor pair. All right, let's look at 19 now. 19, I have 1 and 19. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Nope. 3, 3, 6, 9, 12, 15, 18, 21. Nope. 4, 4, 8, 12, 16, 20, 24, 28, 32. Nope, too high. 5, 10, 15, 20. Nope. 6, 12, 18, 24. Nope. 7, 14, 21. Nope. 8, 16, 24. Nope. 9, 18, 27. Nope. I'm not going to go any higher because I've already gone past what the halfway point would be, right? So if I had 10 then goes to 20, and that's too high. So I know that 19 is going to be prime because we can only come up with that one factor pair, 1 and 19. All right. Pages 163 and 164 are going to be also in our practice page session on Wednesday. We will have our work cut out for us, so please make sure to come right at 10:15 on Wednesday. Pages 165 through 168, you're welcome to do for optional extra practice if you would like to. And that is it for this video then. I will see you guys tomorrow. All right, bye.